13.1 and 13.2 go well together. We've kind of done some similar stuff. We are going to be skipping around a little bit. And you might need some scratch paper. You may not. It depends if you like to write in the graph paper area. If that bothers you to do algebra in the graph part, you might just want a separate piece of paper for today. Let's look at the topics. They're called 13.1, solve a system graphically. And 13.2 is solve a system algebraically. I think it was yesterday we had a problem that was, what was it that went up to 500? Do you guys remember? Or it was in your homework and they might have asked about if something went to 600. You remember that word problem from yesterday? What was that about? Is it a ball? No. That would have been, well.
They're selling candles.
Candles. That's right. So it was the cost that we, the output of candles. Okay, thank you. So let's say I have, I'm not going to do it exactly the same because I don't remember the numbers, but let's say that my graph does this and this right here is 500. I know in my graph that I'm going to sell or make $500. I can tell graphically very easily that I'm not going to make $600 because my graph doesn't touch it. We talked about how to find that graphically just like this. If this equation can be represented by, let me make up an equation, negative x squared plus 7x minus 2. How do I figure out algebraically if that thing is going to hit 600? Right, I want my output, my height, my y value to be 600. So I do this. Then I'm going to move that 600 over. And I'm going to solve probably by the quadratic formula. What's going to happen, because we know our answers, what's going to happen when I'm doing the quadratic formula and trying to solve this? We know the answer, right? Is it going to reach 600? So am I going to get two nice values that equal to 600? What's going to happen here?
Maybe imaginary.
Yes, I'm going to get a negative discriminant, which means there's not a real x, not in any real numbers that have a height of 600. I know this one, maybe at 8, has a height of 500, but no x values have a height of 600. So kind of the same idea. We're doing things today graphically and algebraically. You might know the answer, but you're trying to do it as if you didn't know the graph when you do it algebraically. Let's start with a really basic one. There's kind of a word problem we'll discuss in a minute. Go ahead and look at page 215. These are some you probably did in Algebra 1 or something similar to this. We'll do the first one together. It says, graph each system. A system is just more than one solution, more than one function at a time. Graph each system of one linear equation and one quadratic equation. For each system, list the number of real solutions. So you guys know how to graph the first one. That's linear. Y equals x. Graph that line. Y equals x. It's just like if I were to graph this line. The y-intercept, oh, there is none, so it's 0. The slope there isn't really a number that you see, so it's an imaginary 1. Sometimes we forget how to graph that line. It's a line, intercept 0, slope of 1. Now the next one you can see is not linear. It's going to be a parabola. We know how to graph this. You guys can plot the parent function and slide it down 2. Or maybe we can do it without doing a parent function. Do we know that it's going to start right here? You know how much it's going to rise? Yeah, it's a parabola with no stretch or shrink. So if I go over 1, I go up 1. Over 2, up 4. Over 3, up 9. for basic ones like that with just a left, right, up, down, you don't have to plot the parent function anymore. Now this isn't my answer, this is my graph. The question is, what's the solution to this system? There are an infinite number of points on this blue line, and there are an infinite number of points on the red parabola. The only solutions are the points that they both share. So that's going to be wherever they intersect. So they intersected at 2, 2. And it looks like -1, -1. You can always check it. You can plug in 2, 2 to both of them, see if it works. Plug in -1, -1, and it should work. Is this stuff we've done in algebra before? Graph the system and see where they land. You've probably done 2 linear equations. It's the same idea. It's just a parabola. It may hit more than once. Could they hit one time? Yeah. If I have this and this, that hits one time. Could they hit no times? Sure. I could have this and this. Those are going to hit 0 times. Go ahead and do the next one in your book. Write your answer when you're done. These only hit one time, and that was at 1, -1. Let me know if you have a question about B. If not, go to C. Yeah, I was going to talk about that. So if you're struggling with C, because it says 3x minus 9, there is no 9. Well, let's not plot that point. Let's not plot 0, -9. How about we plug in a 1? If I plug in a 1 for x, what value will I be at? If I plug in a 1 for x, my output is?
-6.
Is that on our graph?
No.
No, let's plot a different one. Let's say I want to start plotting at 2. If I plug in a 2 for x, what value am I at? -3, right? Let's plot that point. 2, -3. Then from there you can plug in values still, or you know the slope is 3, so just rise 3, run 1. Anytime it doesn't fit on your graph, just don't plot that point. Pick the next point on one side or the other. Does that look reasonable, like that's going to hit -9 eventually? Yeah, it does. So it's always good to check and see if it makes sense. So if I said solve this system graphically, we've done this 3 times. Your answer here, there's 2 answers. There are 2 times the graphs touch. There's 1 time the graphs touch. What's my solution here? Are none. They don't touch. So you write no real solutions. There might be some imaginary ones, but none that are going to be graphed on the XY axis. I might not take off if you put no solution, but it should say no real solutions. Okay, we're going to do these same 3 problems algebraically. We should get the same answer. Pretend you don't know the answer because we want to make sure we can do it both ways. So how do I do this algebraically? I'm just going to do it right there. You can do it wherever it works for you. Algebraically, let's take a look. I have this system. If y equals x, then instead of a y here, I can just input that x. Since x is equal to y, I can just substitute it in there. So it's going to say x equals x squared minus 2. Just like solving by substitution, elimination, we're solving this one by substitution. Y equals x, and here's a y. I'm putting an x. Okay, let's solve this. I'm going to move the x over so that my x squared stays positive. Good habit to get into. You want your x squared usually to be positive. Do you think we could factor this one? Yeah, I think we can factor. We need numbers that multiply to 2, so that's a 1 and a 2. Could that add to a negative 1? Yeah, 2 is negative, 1 is positive. Okay, set each piece equal to 0. Is this my answer? Negative 1, 2? No, look closely. That's x equals and x equals. So x is negative 1. I have another x that's equal to 2. How do I get the y coordinate? I plug this x into either equation because it should match for both. So plug it into the easier one. X is equal to y. Same answer algebraically. Okay, go ahead and set your pencils down, please. I'm going to show you just because sometimes you will be doing the quadratic formula. Let's say you did the quadratic formula here. Opposite of b plus or minus a discriminant over 2a. The discriminant is b squared minus 4ac, which is 1 minus, hold on, b squared minus 4ac plus, there we go. So that's 1 and plus 8, so that makes 9. That's a good discriminant because that's a perfect square. So that's going to be 1 plus or minus 3 over 2. 1 plus 3 over 2. 1 minus 3 over 2. 1 and 3 is 4 over 2 is 2. 1 minus 3 is negative 2 over 2, which is negative 1. Can be done either way. Notice my discriminant was 9, which is a perfect square. So I'm going to get 2 answers that are real and rational. Let's try letter B. You can pick up your pencil again. We're solving, so probably going to do elimination again. So I'm going to substitution again. I'm going to substitute that. Because that's equal to y, I'm going to put it right there for y. So 2x minus 3 equals x squared minus 2. Go ahead and get everything to one side. You can factor, but I am going to do it the quadratic formula because I want you guys to see something. I want you to factor when you recognize it and you can do it quickly. But that's the way I would have done it. But I wanted to show you this. Here's my quadratic formula. Opposite of b, I'm going to do the discriminant down here over 2a. My discriminant, b squared minus 4ac, is 4 minus 4, which is 0. Did you anticipate that? Because how many solutions are there? 1. The only way to get one solution with a plus or minus, because plus or minus always is two different answers, except for 0. Positive 0, negative 0 is the same thing. So this turns out to be 2 plus or minus 0 over 2, which is 1. So if you were doing this algebraically, then you would have to take your x of 1 and plug it into either one you want. So 1 squared is 1, minus 2, negative 1. What is going to happen to this last one when I solve it? What is my discriminant going to be? Negative. We don't know the number yet, but it's going to be negative. Let's try it. So again, we're solving. Let's substitute. That's y. Put it in for y. So my equation was 0 equals x squared minus 3x plus 7. So quadratic formula, 3 plus or minus root negative 19 equals 2. I'm going to simplify that just a little bit. I'm going to put I root 19 over 2. And I might say no real solutions still, but I can put that those are my imaginary solutions. So we've kind of done both lessons already. 13.1 is graphically. 13.2 is algebraically. What we haven't done is a word problem. So what we're going to do is we're going to look at a word problem that your book talks about, and it will be something like, I think it's about supply and demand. You've probably heard of supply and demand before. So it's going to say, here's our lengthy function that they're going to give you that says, here's how we figure out the supply. I think it's about haircuts. This is how many people supply. So this is how many people we have to give haircuts. This is our supply of people who cut hair. Then it's going to give you another function that says, this is the demand. These are the number of people that need a haircut, or a function that can determine that. We want to know when the supply meets the demand. Otherwise, they'll be too high. We'll have too many people that need a haircut, not enough people to supply it, or vice versa. Okay, so it's going to be the same idea. You're going to get two functions. And we, if we're doing supply and demand, we want to know when those are equal to each other. Is it going to be a nice, pretty graph like this? No, this is real life. We're talking weird numbers, but you're still going to graph it. And then we're going to do it algebraically. The graphs, however, are probably going to be on your calculator. So let's take a look at page 211. There's a lot of reading, but we only have one problem left. We're doing one problem graphically and algebraically. Who wants to read page 211? Shelby, you want to read it? I know you weren't raising your hand, but would you like to read?
Sure.
Thank you.
The owner of Salon Ultra Blue is working with a pricing consultant to determine the best price to charge for a basic haircut. The consultant knows that in general, as the price of a haircut at a salon goes down, demand for haircuts at the salon goes up. In other words, if a Salon Ultra Blue decreases its prices, more customers will want to get their haircut there.
Thank you. I'm going to read the next one. Based on the consultant's research, customers will demand 250 haircuts per week if the price of the haircut is $20. For each $5 increase in price, the demand will decrease by $25 per week. Could you write an equation for that? Try to, just off to the side there. It's linear. I'm going to go with point slope as my approach to this problem. We know there's this type of line, that form, standard form, or not standard form, slope intercept form, but I'm going to go with point slope. I need a point and a slope because I don't have the slope and intercept. Because it's a word problem, I'm going to write what X and Y represent. Well, you guys tell me, what is X and what's the outcome Y? What is it?
X is the price increase.
Yep, so it tells you right here. Well, I would say the price of the haircut. So X is cost of haircut. And then Shelby, that's going to determine the output, which is?
The amount of customers.
Yep, F of X, which is your output, models the quantity of haircuts needed. So number of customers or something like that. Let's put the number at the end. So if you read this, we have a point. It says, based on the consultant's research, customers will demand 250 haircuts. That's how many are needed per week if the price is $20. So at a specific X of $20, we have a specific Y, 250 haircuts. They could have said, if you charge $10, there will be 80 people that need a haircut. Whatever they give you, write that down as your point. If the cost is 20, 250 people will need their haircut. Now I need to find the slope. Remember, slope is the change in y over the change in x. Now let's read this last sentence. For each $5 increase in price, the demand will decrease by $25 per haircut. That's your slope. Demand. How much is the demand going to change? The demand will decrease by 25. So the change in y is down 25. What will that be for the change in cost? $5 increase. So add 5. So my slope is -5. I don't care how you find your answer, but this is how I did it because when I read the problem, I noticed a specific point was given. Questions on what I have up there? Let's fill in your point and your slope. So y minus y equals m x minus x. You can leave it like that, but let's go ahead and get y by itself. So this is one of your equations. Make sure you don't lose it because I said we're doing something like this. So this is one of our equations that we're going to graph. And this is for demand. It's for the demand of haircuts. I'm going to tell you the supply function because it's not something I would expect you to find. So next to this, you can write demand. And here's the supply function. Y equals 1/10 x squared minus x minus 5. I'm not going to have you graph that on paper. I'm going to have you graph that on a calculator. So go to your y equals and you've got 2 things to plug in. If you're borrowing mine, try to clear it when you're done. So next hour it's not already in there. My window's still set at 600 from the other day, so I'm going to put it back to -10 to 10. We'll see what it looks like. -5x plus 300, 350. I'm going to put my 1/10 in parentheses, just to be safe. I just put it back to 10 just for now. We'll see how our window looks. I doubt our window's going to look good because we're in the 350s, but let's do a -10 to 10 window and see what it looks like. Ooh, this is what mine looks like. I can't see the line. So I'm going to go ahead and zoom out. Let's see. I don't know. Let's go. Well, you guys tell me. Sometimes people don't know what to do with the window. Any guesses? What should I do? It's not really right or wrong. You do it. If you don't see what you want, try something different.
Since this is a word problem, and in order for it to make sense, I know that x or y can't be negative.
Okay.
So I have my x minimum at 0, and then since it goes so high, x maximum at 500
Okay.
with a scale of 20, and then my y maximum.
Okay, I'm not going to change my scale just because I never do. 500. So you have yours going up by 5s. By 20s. Oh, okay. I'm just going to do 1s. Woo, look at my graph. I went to 500, and that's way too far. So I'm going to move mine to 100. And the x. Ooh, still very far away. But they don't intersect, so let's do the y. They know they're going to touch up at the top. So let's go to a different height value, a different y of, let's try 400. Oh, there they go. You just keep trying things until you get what you want. If you want to go higher in the x or y, change those. Now, Jonathan brought up a good point. These are going to intersect 2 times, but because of the word problem, we don't want negative dollars or negative demand. So we only care about that. I can go ahead and zoom out so you can see the rest of it. Zoom out a lot. Goodness gracious. This is a, yeah. I just always tell people not to change the scale, so that's what I did. Okay, so if you did keep zooming out, making your scale bigger, you could see the 2 intersection points. But again, we don't care about this one for the word problem. If it weren't a word problem, we would have to keep zooming out, changing our window until we found that. As long as you have one, you're good. Here's how you calculate that graphically. Does anybody need more time to get at least that intersection in their window? Okay, so we gotta go way over there. So that's x direction. We don't need negative 200. Let's do negative 10. We're not doing any negatives. And the x direction, sure, try that. See what happens. Okay, so you can tell they're gonna intersect up there. So you want your y to be higher. So the y value. So the window, your y is at 10. Let's go like 500. There we go. Now you can zoom in more if you wanted to see it more in the center, but as long as you see the intersection, good. Okay, so everybody go to your graph. Yep, go back to y equals. And then you gotta turn those plots on. So go up and enter, over, yep. Those are stat plots, so we don't need those in there. The first stat plot was still on. Now graph. Okay, here is how you calculate. We've calculated min and max before. It's kind of the same idea. So hit second. Oh, I didn't hit second like I just said. Second, calculate. We're not going to calculate the min or max. We want to calculate the intersection. Hit enter. Now there's a cursor on my Y1. I'm going to move my cursor till it's about at that intersection point. I could try to get it right on top. As close as you can is fine. You're moving your cursor until it gets to that intersection point. Not the left or right, but like right on it. Hit enter. And then it'll allow you to move your cursor on the Y2, but it'll normally be right where you want it to be. So hit enter when you're there. Do we want to guess? No. Enter. That is your intersection point. It's not nice and pretty because, again, it's a word problem. Let's write this point down in your book. 42, this is money, cost of a haircut. So $42.85, $42.85 for a haircut, comma, I guess this is how many people we would get. 135 point, what's a person? So 136 people about. How many you would get? We're going to do this in just a second algebraically. If you need help with your calculator, I can help you when we're done. I don't think I'll have time to come around and look at all of them. What's yours doing? Did you do the right intersection point? Because if you did the other one, that's definitely a negative x. I'll have to come look at it, but I don't know if I have time right now. Okay, let's write these functions. We're going to solve these. How did we solve these questions? Here, we substituted. So let's substitute again. This is where you might want some scrap paper. If this equals y, then you're going to plug it in for y. We're kind of done with our calculators unless we need them for algebra. So let's substitute that for y. Now, we haven't dealt with 1/10 much. Should we just get rid of the fraction? How do we get rid of 1/10? Multiply by 10. So I can't just multiply one number or one side by 10. I need to multiply this side by 10 and this side by 10. That's an easy number to multiply by. So just like you did before, get it equal to 0. Do the quadratic formula. Quadratic formula is going to give you two answers. One's going to be negative, which we don't care about. All right, Jay, I can come look at your calculator. You fixed it. Okay. It's a word problem, so you can do decimals. What was their calculator during this? 46 somewhere around this? Did you write down that point? The intersection point on the calculator?
I think it's like 46.3 or something.
Yeah. The one that our calculator gave us when we did the intersection, it wasn't a nice number.
So we rounded.
But the money could round to hundreds. What was it?
42.89.
Let me check my math.
Wouldn't it be 3,550 instead of more?
Ah, that's why. I knew they should come out to be the same number. So. Yep, 3550. Thanks. $42.85.
Yeah.
But if you type this all in, make sure you hit enter or parentheses. Don't just hit divide by 2. It won't work. Enter or put the top in parentheses. You will get another answer. but that doesn't make sense in this problem. Don't forget, you're running out of time, so I won't have time to finish it, but that only gives you the X part of your answer. You would have to plug that back in for Y. I'm going to have you ignore the directions on the homework. It says, it's not 9 and 10. Do it graphically and algebraically because it's all from the same section. So if it says solve graphically, solve them both ways. That way I don't have to give you problems from both sections. If it's a graph one and it's a word problem like that, you can do that on your calculator. You don't have to graph it by hand.